Now we want to look at the basic properties that functions can have. So first of all, let's just remind ourselves what the graph of a function is, because this is going to be the most effective way to understand, I think, what various properties of a function mean. So throughout the rest of this video, let f be a function. So remember, that's some sort of rule which assigns to every x in the domain a unique number f of x in the range. So just recall how the graph works. It's a really neat idea. The basic plan is to visually interpret this using the xy plane, where we think about the x coordinate as the input and the y coordinate as the output. So if I draw the xy plane to start off with, and then I draw a graph for a function. So who knows what it looks like? Something like this. It's actually a pretty bad graph because of the turn there. I'm violating the vertical line test, so maybe something like this. A bit better. Okay, so we're thinking about this as y is equal to f of x. So this really, y equals f of x, is the algebraic description of this graph, if you want. Okay, so this is the graph of f. Okay, so what does it really mean? Well, if I take a point on this graph, let's say here, there are two numbers associated to it. First of all, the x coordinate, and then the y coordinate. So if at the bottom here, the x coordinate is just x, the y coordinate by definition is f of x. So we're basically plotting all points in the xy plane where they're of the form x comma f of x, where x is in the domain. Okay, so this is what the graph is. So the graph allows us to visualize a lot of important properties of a function. Let me write that down. So it allows us to visualize many important properties. Of a function. In some ways, it's the best way to represent the information of a function, just because it's very immediately clear visually what the behavior of the function is. So let me do kind of everything by example, I think. Let's start off with the following example. So first of all, let's draw a graph of the form, so we'll do x, y. I'm going to do two examples, so let me just duplicate this. Okay. So the first one, imagine this is what my graph looks like. Something along these lines. So this is my y is equal to f of x. Algebraically written. So I can see here something kind of special happens. First of all, there is this position. I'm going to mark with a red dot here. So this position, let's say it's a on the x-axis, some fixed number there. So this position is called an x-intercept. Not surprisingly. Not surprisingly, because of the fact we're intercepting the x-axis. Okay, maybe another point worth pointing out is here. This is called the y-intercept. And the y-intercept is actually very simple. All it corresponds to is where, well, it's the value of the function at 0. So there's not much to say about that. But the x-intercept is a lot more important, because at the x-intercept what's going on is you have a situation where the function, the y-coordinate is 0. So the x-intercept is exactly the position, or it's a position where the function is equal to 0. Something we definitely know is important, right? We've seen lots of examples in the past of expressions in x that we need to solve where we might try to set them to be equal to 0 and try to solve. So finding solutions of things like quadratic equations, for example, is very related to x-intercepts and that kind of thing. Okay, so maybe kind of directly below, what I can conclude to some extent from this is the following, just from the picture. I mean, f of a equals 0 if and only if the graph y equals f of x intercepts the x-axis at x equals a. So intersects. Should I say intercepts or intersects? I don't know. I'll do this. Intersects the x-axis at x is equal to a. Okay, so if I have a function and I have the graph and I can see where it crosses the x-axis, that tells me the zeros of the function, first and foremost. It's a very nice visual way of thinking about a zero of a function. It's where it crosses the x-axis. The y-intercept, where it crosses the y-axis, is much less interesting because all that is the value of the function at 0. Not so interesting. Okay, so let's imagine now I have, let's say, two graphs. So let's have the same basic story, something like this. Dot, 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 dot. Y is equal to f of x. And let's have another graph. So another function, and let's imagine something like this happens. Dot, 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 dot. So this is y is equal to g of x, where g is another function. So from the way I've set it up, what's happened is I have another kind of interesting position here, a cross point. So this is the position where the two graphs intercept each other, or intersect. Now what's the meaning of that? So let's maybe label a point. Let's label this point. Should we label it B at the bottom? Maybe that's better. I don't want to call it the same as A because A was the x-intercept of F. Now what does that mean? Well, where they intersect is where the y-coordinates are the same. So that means that at B, the output of G and the output of F are the same. So what can I see? Well, if I try to kind of write this a bit more formally, this is basically the statement that G of B, or sorry, F of B is equal to G of B if and only if the graphs intersect at this point. Graphs y is equal to f of x and y is equal to g of x intersect. So they share the same point at the point x is equal to b. So if I want to know positions where both functions have the same value, the same output, that is exactly the same as crosses, right? Positions where the graphs cross each other. So these are two kind of important things to understand about what you're seeing when you're seeing functions. So the points where you cross the x-axis, so can I do this? Maybe I'll join these two together into a conclusion. They kind of feel very similar to me. It's going to work? Something's going to work. What happened here? Oh my goodness. So maybe just to kind of separate these a bit, because they are a little bit different, but they're very similar in flavour. So the points where the graph crosses or touches the x-axis, that's the values of the function being 0, important. And if I have two functions, the positions where they cross each other or touch each other is the positions where they're identical to each other, they're equal to each other. Now, this is important. When we're talking about functions being equal, we've already discussed this. Two functions being equal as functions is much, much, much stronger than this. Two functions being equal as functions is the statement that they have exactly the same domain, and for every input, the outputs are the same. So essentially, two functions are the same if and only if their graphs are completely identical, right? This is not the case here, right? So maybe what I should call this is not equality of functions, but pointwise equality. Maybe that's a kind of a nicer way to put it. Pointwise equality. So two functions being equal at a point, it's significantly less strong a result. Right? These are definitely not the same functions because they have different graphs visibly. Okay, so this is nice. So we can spot this information. Other information we can see from the graph, when you are above the x-axis, so when the graph is above the x-axis, so I'll just say this because it's very obvious. So up here, for example, when you're above the x-axis, you're positive. So f of x is greater than 0 if and only if the graph is above the x-axis. Similarly, f of x is less than x0 if and only if it's below the axis, like here. So in this example that I've drawn, if x is strictly bigger than a, I'm positive. If x is strictly less than a, I'm negative. So I don't think it's necessary to write that down formally. Something to be aware of. All right, so let's do another example. Okay, so let's take basically the same story as I've just done, at least the same basic picture. So again, I'm going to do two examples. So let's duplicate this. Okay, so let's do one that's incredibly similar to what we just did. Something like this. Okay, so again, let's do y is equal to f of x. In fact, maybe I shouldn't use this notation because I'm going to have two different things going on. All right, so first of all, let's take this graph and let's take another graph. Let's do one that's really quite different from the looks of things. Let's do, so I'm going to label in this one some positions in the axis. Let's do -1 here, 1, 2, let's try and do this accurately, 3, 4, 5. All right, so now let me draw some stuff. Okay, first of all, generally when you look at this, you might be like, wait a minute, these don't match up at all. They are both completely valid examples of functions, but there is a bit of a difference between the two of them. The first has a nice kind of continuous domain, if you want, and you can see in this one, from at least the way I've drawn it, the domain in the first example is all real numbers. It seems to me that every single x coordinate is accounted for. This guy, though, on the right-hand side, very different. The only positions that seem to matter, and maybe I should include one more point for 0. In this case, the domain is, well, the only possible x coordinates that turn up, or x values, are, it's not very many. It's just -1 to 5, and it's only whole numbers. So this is just an example of a graph of something where the domain is discrete, if you want. So it'd be -1, 0, 1, 2, 3, 4, 5. So it's a discrete domain. Now, there is something about these two graphs that's very similar, though, in the sense that as I move from left to right, so as I allow the x to increase, if you want, the output of the function goes up. So this is true in both cases. So as I move from left to right, the output of the function seems to increase. So let me state that a little bit more precisely, shall I? So in both cases, if I, for example, well, let me just write this down. So in both cases, so I'm assuming both of these could represent the function f, let's say. So fx increases as x moves to the right. It seems to happen in both cases, right? It seems to go up. So let's try to make this more precise, shall we? So imagine I've got two positions. Let's say A and B. In fact, let me do them a little bit closer in so I don't have issues with the y-axis. Okay, so let's imagine I have an A and a B here. And the way I'm setting it up is A is less than B. So what seems to be happening is, as I move from left to right, the output of the function increases. So this, of course, is f of A here. And this, of course, is f of B by definition. But notice f of B is bigger. So I'll write it like this. It's a bit of a strange way to write it, but it's bigger than that. So that's me writing kind of an inequality on its side. So how can I explain this concept of increasing as I move from left to right super carefully? So let's try to kind of precisely capture this. So definition. So I'm going to come up with a super precise statement which captures exactly what's happening in both cases. What I've just drawn, this A to B and then FA to FB, is exactly the same on the other side. You've got a bit less freedom about your A's and B's, obviously, because the domain is much more restricted, but you have the same basic picture. So definition. In fact, let me do this. So we say f, my function, is increasing. So it's an increasing function if, now the first thing about this is it's a statement about the whole domain. If for all A and B in the domain, so any A and B I choose, well, if I take A strictly less than B, this guarantees that f of B is strictly bigger than f of A. In other words, this function preserves the inequality. It's kind of neat. We've talked a lot about preserving inequalities with algebra, and now this idea is kind of popping up with the idea of an increasing function. Okay, so this is a definition. Let's make sure it's in a box. So when I say definition, this is the meaning of increasing. It's the meaning of increasing. This is a precise statement, a precise description of a concept. So two ways to view it. Intuitively, it means as you move from left to right in the graph goes up. But really, really concretely, what it's actually saying is essentially the function preserves inequalities, at least for A and B in the domain. So it's very important you understand that this is true for all elements in the domain. If it fails for any 2 points, it's not increasing. So let's do an example, shall we? Let's do an example. Something you're going to immediately notice when you start doing university mathematics courses is concepts that perhaps you were kind of familiar with intuitively before. Suddenly you'll realize actually you were much more shaky on them than you realized, because you need to have totally crisp statements about things in order to really understand them. And this is just a good example. This statement about one inequality implying another seems terribly difficult, but it actually is the true meaning of what increasing is. So example, let's take f of x is equal to square root of x, shall we? Let's take a moment. What's the domain of this guy? Well, the domain is, by convention, all x such this makes sense, and that's all non-negative numbers. Now, what do we know? I need to check that this condition holds. So if I'm going to show it's increasing, that has to be true. So I've got two options, I suppose. One, which is only kind of, it's pretty imprecise. I could draw a graph and then check it's moving up as I move from left to right, but that wouldn't be mathematically precise because I can't, for example, draw the entire graph. I can only draw it for a bit. So even if I do draw the graph, I don't have a totally airtight reason that it's increasing. To have an airtight reason it's increasing, to be completely certain, you need to show that this is true for any a and b in the domain. So let's check it. Is it true? Is it obviously true? So let's take, so let me write this carefully. Let's take 0. So let's take a and b in the domain, so they've got to be greater than or equal to 0. This guarantees, if I take the square roots, it preserves the inequality. Do you remember when we did the properties of inequalities? This was one of my properties of inequalities. It was the second from last one. It was the fact that if you take roots, it preserves inequalities. This is kind of a nice full circle moment. So this is just a property of inequalities. So what do I conclude? Well, I've checked the defining property. F is increasing. Very nice. So if I say to you now, is this function increasing? If you want to really, really persuade me, what you've got to do is take any 2 points, A and B in the domain, where A is smaller than B, and show that f of A is strictly less than f of B. If you don't do that, you're basically purely relying on a hand-wavy argument when it comes down to it. I.e., look at the graph, it all seems to work out. That's not university mathematics. You need to be completely and utterly sure, completely certain. That means you must check the defining property. So there's a bit of a jump in the way we do things at university, and it does take some time to get used to. But I think this is kind of neat, right? So we started off with a picture that made a lot of sense, and then I took the picture and kind of boiled it down to its rawest essence, which is the definition, and then I observed that we can check functions we're familiar with. Square root of x is a function, are increasing, and essentially it just comes down to one of our properties of inequalities, or algebraic properties of inequalities. So neat. So the flip to this, obviously, is instead of going up, you could be going down as you move to the right. So let's do a picture of that. And I'll kind of mix things up to give you examples of graphs that are kind of a bit unpleasant. We've already seen a few of these, but I'll do another one. This one's pretty nasty. So let's take a graph like this. All right, so imagine this is my graph going down, 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 and then just to be a bit nasty, I'll have, let's say, a solid dot there, and I'll drop like this. Now that drop is kind of unpleasant, but I still have exactly the same thing going on here, I think. So let's take the same basic approach as I had before. Let's imagine I have, let's make this quite small so it's visible. So imagine I take an A and a B, and let's just think about what the outputs of the function have to look like. So let's set it up so that A is strictly less than B. So the position in the graph over here would be what? This would be f of B. And here would be f of A. Is that right? And notice now it's the other way round. This f of A is now bigger than f of B. So if the graph So what we're seeing here, intuitively at least, is f is decreasing. Or f of x, sorry. Let's be careful. F of x decreases that value as x moves to the right. It decreases as x moves to the right. And if I'm going to try to capture this precisely, I think I kind of have exactly the same thing. So, albeit with one of the inequalities flipped. So definition. So we say f is decreasing is a decreasing function if for all, so again, subtle, it's for everything, for all a and b in the domain, if a is strictly less than b, like in this picture, then f of a is strictly bigger than f of, is strictly bigger than f of, what is it? F of b, sorry. So now it's inequality reversing. So the inequality is reversed. It's a bit of a mess where I've written it. Reversed. So that is my diamond precise meaning. Oh my goodness. That is my diamond precise meaning to decreasing. And it's exactly the same, but it reverses the inequality. So let me do an example now, just to show you of how familiar this idea is. So let's do a really simple example. Let's do f of x is equal to minus x. F of x is equal to minus x. Now, is this increasing or decreasing? So before we go anywhere, what's the domain? So the domain is all real numbers. And I want to show it's either increasing or decreasing. So I'll kind of skip ahead a little bit. I'm going to graph this, show you what the graph looks like. You may well know what this looks like, but I'm just going to illustrate it to you just so that we ahead of time know what it looks like. The graph looks like this, actually. So it's a straight line, kind of going down as you move to the right. So looking at this, I'd say, well, it's got to be decreasing. But can I actually prove it properly, right? So we've got to take any two a and b in the domain. So let's have a less than b, absolutely any numbers at all. No need to be positive because minus x makes sense for anything. Okay, so I need to show that the inequality is reversed. So what am I doing? I'm taking minus. So taking minus of something is the same as multiplying by negative 1. So if I multiply by minus 1, minus 1 is negative. And one of my fundamental properties of inequalities is that it reverses the inequality. So this is really neat. So this is kind of a property of inequalities. Brackets minus 1 is less than 0. But we know that minus 1 times a is equal to minus a. So this is the statement that minus a is strictly bigger than minus b. But that's exactly what we need. That's this completely. Because, so to really do this carefully, f of a is minus a. And minus b is f of b. So that statement guarantees that statement. And it reverses the inequality. So isn't that neat, right? You're probably very used to the idea of the graph of y equals minus x going down like this. but you can really see it from your core properties of inequalities. That's really the case, why it's decreasing. Something as well I want to say about decreasing and increasing. I think a lot of people, when I teach this, think that increasing and decreasing has to do with the slope of the graph. So that's a concept which we've not covered yet. But if you think that increasing or decreasing means the slope is positive or negative, you're wrong. In the following sense, the concept of increasing or decreasing is broader. Let's go up here a second. Right? This graph, there's no slopes. It's weird. It's a bunch of kind of fragmented dots. There's no slopes at any point here, but it's increasing. Right? Increasing is a broader concept than the idea of the slope of a function. So if you're looking at this and thinking, trying to match it up with your knowledge about positive and negative slopes, don't, right? You shouldn't be thinking about increasing and decreasing with those. That turns up in calculus, but the concept of increasing and decreasing is more general than the idea of increasing or positive or negative slope. That's just something to say. It's a really, really broad idea, and it's purely to do with these statements about inequalities. So again, if you are doing kind of algebra with inequalities, the basic story is if you have an increasing function, you know it preserves inequalities. Brilliant. If you have a decreasing function, you know it reverses inequalities. If it's neither increasing or decreasing, then who knows what happens, right? It could be a total mess.